Hello again, my name's Eric. We're going to do some calculus today, and specifically we're going to take a look at solving differential equations that are separable, which lead to exponential growth or decay. And so this is a popular topic in a first-year calculus class. It gives you a chance to play around with the differential equation and also to do some growth or decay modeling. Hope you like this little cartoon my daughter sent me this morning. Now let me show you the problem that we're going to tackle. Okay, this is a biological half-life problem. This comes out of an old Paul Forster calculus book, which I'm very fond of, mostly because he's got some really good problems and really good applications. And here we have somebody who inadvertently inhaled some kind of a poison and decides to go to the doctor. And the doctor measures the concentration of poison in the victim at 0.00372 milligrams per milliliter and says, come back in 8 hours, and measures again. And this time she measures the concentration at this value. So as you can see, it's decreasing. The concentration of poison in this person's blood is decreasing. Now these measurements are 8 hours apart. So you can assume, since he waited 20 hours to go to the doctor in the first place, the concentration was probably a lot higher when first inhaled. And that's one of the things we're going to answer is, how bad was it in the worst case, which was when the poison was first inhaled? And was it high enough concentration to put this person in any kind of danger? See, real life things that can be answered by solving calculus problems. Now, I hope you had a chance to look that over. If not, you can pause the video. If you're taking notes, you can rewind, whatever. I'm going to make this disappear and work through the problem. The assumption of this problem, like the one I did in the previous video, is that the concentration of the poison changes at a rate proportional to how much poison is there. Anytime that's true, and you solve the separable differential equation, you're going to find that this variable changes exponentially. And to take you through that, I'm going to get a nice background, because obviously this is large enough for you to read, but it leaves me no space to work. So let's do that. Okay, key statement here is, from biology, realize the instantaneous rate of change of poison concentration with respect to time is directly proportional to the concentration of the poison. And they're suggesting that we use C for concentration. I'm going to use P for poison, okay? But the original statement can be written something like this. Rate of change of poison is proportional to how much poison there is. In other words, if it's very, very concentrated and it's decreasing, though, it'll decrease at a higher rate. Later, when there's not much of it left in the body, it'll continue to decrease, but at a lower rate, because the poison and the concentration are proportional. Well, to separate something like this, we'd like to get all the p variables and p differentials on one side, and any kind of a t variable or t differential should be on the other side. You saw me do this in the previous video. I'm going to go a little bit faster this time. Multiply both sides by dt and cancel the dt's. Now divide both sides by p, like this. Cancel these p's, and you now have something like this. It's separated and it's ready to solve. Most of my students are now going from here to here in just one step. Okay? First step is separate. Second step is to integrate or do antiderivatives. So it looks like this. I want to explain why it is that the antiderivative of this is kt. Remember, k is a number. So this is just a little aside. When you take the derivative with respect to t of any expression of this form, where b is a constant, you just get an answer of 3. This is a linear equation. It's got a constant derivative. So the antiderivative of this constant would take you back to a linear equation. Now, take the 3 out and put a k there, where k is some constant, and the same thing is true. The derivative of kt plus b, where k and b are constants, okay, with respect to t, time, is still going to be k. And that's why the antiderivative of k is k times t. The antiderivative of 1 over p is the natural log of the absolute value of p. You'll need a constant of integration either on the left or on the right. It's pretty typical, common practice to put it on the right side, and you don't need it on both sides. Separate, integrate, get the correct antiderivatives. Now do algebra until p is isolated. The goal is to have a closed equation for poison concentration, p. P is an absolute value, but it's also inside a natural log. So to release this from this log, we're going to treat each side of this equation as an exponent sitting up above an e. And that would look like this. I call this step exponentiate. And the purpose of this step was to use inverse properties of exponents and logs to get this p almost completely isolated. Now I'm going to go ahead and work on the next step here. I call this step manipulate, just because it kind of rhymes with the other steps, but you're going to use a property of powers here to rewrite this power as a product of powers of e. One of those powers looks like e to the b. I'm going to put it here. The other one looks like e to the kt. Separate, integrate, exponentiate, manipulate, designate. I've got this letter C here. It represents a constant, and I'm going to give them a job to do. You will represent e to the b. Designate. Not a necessary step, but it makes for a cleaner solution. So now I have this. And last but not least, I want p not to have absolute values around it. There's a concern though, you know, everything over here is positive because both of these factors, if you look back here, are powers of e. Every power of e is a positive number. And so if you take these absolute values off, you might be equating something positive with something negative. And that is why, and it's important that you write plus or minus over here. Okay? Lots and lots of variables change in a way that's proportional to how big the variable was in the first place. And they all end up having a solution that looks like this. And this is a general solution, okay? Now, if you can tell me what C and K are, you can make this what's called a particular solution. So here's where we have to read carefully. They want T to be 0 upon the first doctor visit, where the doctor measured the concentration and it looked like this. So this is T in hours. This is concentration of poison, and let's get the units right. This is milligrams per milliliter, I assume, of blood. And in the beginning, when you had, that might be out of the camera. Let me move that over just a little bit. Okay, in the beginning, when you first went to the doctor, they set the clock to 0, measured the concentration of the poison, and it was this. That's 372 hundred thousandths. milligrams per milliliter. 8 hours later, when you went back to the doctor, the concentration had dropped to 0.00219. You're going to use the initial condition to help figure out what this C is. Now I'm going to make all the rest of this work go away because I need some space. I'm going to write our general solution up here. And the first thing I'm going to do is work on figuring out what is C. What is C? You're going to use time equals 0 and concentration of 0.00372 and plug those in. K times 0 is 0 and e to the 0 power is 1. So it must be the case that this C is positive and equal to that. All right, one down, one to go. We know what C is now. So what you want to do next is figure out what K is. This is sometimes called a boundary condition. Just additional information that you're going to need to figure out what K is. And that would look like this. You plug the poison concentration in here. And you plug 8 in for time. And then do algebra and use properties of logs and exponents and solve for K. So I will divide this by that. And I went ahead and multiplied each one of these by 100,000 so I didn't have to deal with those decimals. And anyway, it's a correct ratio. I'm going to take a natural log on both sides. For the purpose of using the inverse properties of logs and exponents. So now I'm almost done. I've got natural log 219 over 372 equals to 8K. Divide by 8, we're done. So it's probably good to have a calculator hanging around. I like this TI-84, it's very easy to use. If you are a Android phone owner, I believe you can still get a free app on your phone. It's called WabbitEmu. That's right. And this phone will set up basically a duplicate of this calculator. This app will set up a duplicate of this calculator on your phone for free. I run it. I love it. You can program it. You can graph with it. You can do everything. So let's compute this now. So natural log 219 over 372 divided by 8 negative 0.66 2277656. You honestly want to keep as much of that decimal accuracy as you can. Don't round it off to the hundredths place. Don't truncate it. Although it does basically mean that you're going to lose about 6.5% of your concentration of poison every hour. That's what the meaning of it is. But there's a button here that says store, and you're going to hit store alpha K. And then it confirms that it was stored. Then you're going to hit y equals and type this in. but not until you have first stored this as K. So I already have mine typed in because I set this up ahead of time and I don't want to go any slower than I have to here. If I pull up Y1 by using the vars button and evaluating it at 0, I get this answer, and I should. And I'm going to evaluate it at 8 to make sure I get that answer. And I do. So now I know it's working well. So we're up through part B here. Part C says, the doctor says you might have had serious body damage if the poison concentration had ever been as high as 0.015. Based on your mathematical model, was the concentration ever that high? Well, here's something you don't do every day, but if you think about it, it makes sense. You can use this model retrospectively. In other words, we get very used to plugging into equations to predict things that are going to happen down the road. But in this case, we want to know what happened in the past. Well, what would you put in the table for a time to represent 20 hours ago? Yes, you'd put -20. So what we're going to do is evaluate this at time -20, and you're going to get a concentration higher than either one of these. So here's what's going on. If the concentration of poison is here, and time is here, you're at about level 0.003, and I'm just rounding things off. It's actually closer to 4. So 8 hours later, the poison has diminished to 0.002. That's almost a halving, almost. But the question is, what about 20 hours prior to all that? And I did some computing with this before I turned on the camera, and it turns out that the poison was about 4 times as high as that. Now, all you have to do since you have your model set up is plug -20. So I hit the vars button, which is close to clear, tab to y-vars, hit enter for function, hit enter for y1 because that's where I have this stored, and evaluate at -20. And it says that the concentration was 0.13989, which is below what the doctor said would have been a dangerous level. Oh, I'm missing a 0 here. Excuse me. There we go. That's the correct answer. That's below 0.015. And so you came close, but it looks like you're going to be all right. Okay? Plot the graph. Sketch the function. That's pretty good. Although typically, if you're gonna make a graph, you should indicate what the units are. And so this is milligrams per milliliter for units, although it doesn't tell us what the poison is in the first place. Okay, part E. The biological half-life of a poison in the body is the length of time it takes for the concentration to drop to half its present value. So you could pick this to be the present value and then try to figure out how concentrated would it be when it's half of this, and then go back and solve for time, and you will know the half-life. So what you'll have to do probably is take a calculator and divide that in half. So 0.00372 divided by 2 is, of course, 0.00186. So what we'll do is we'll put 0.00186 into the poison side of the equation. We'll set it equal to 0.00372 e to the kt. And remember, we know what k is, and it's stored in our calculator. Okay, how do you go about solving this? you divide both sides. And there's a time saver coming up I'll talk about, but we're going to go ahead and divide both sides by 0.00372. And if you actually go through the effort to type this into the calculator to divide it, you may be surprised that it comes out to 0.5. Well, all half-life problems come out to 0.5 at this step. Now take the natural log of both sides. In order to cancel the exponential. And now you're down to here. And if you want to know the half-life, divide both sides by k. And if you want to know a shortcut for half-life problems, they always come down to natural log of a half divided by whatever the decay rate is. That's it. So if you're in a hurry and you're taking a test and nobody's looking at your work, maybe it's multiple choice, got a half-life problem, just do that. Let's see what that value is. Log 0.5 divided by k. Turns out to be 10.466 hours. So at 10.466 hours, you would expect that the original amount had halved itself to 0.00186. By the way, sometimes when you're doing exponential growth problem, one of the questions that gets asked is how long does it take for your money to double, if you're counting money? Or how long does it take for your money to triple? Well, guess what? A doubling problem is just like a half-life problem, except you have a 2-year instead of a 0.5. So there's a shortcut for you, and that concludes this problem. I think I'm going to conclude the video here. Again, my name's Eric. If you're my student, I miss you like crazy, but if you're not, I hope you learned something. Goodbye.